Okay, so get this right. Imagine like this tech that can listen to just a tiny bit of someone's voice, like, I don't know, a 1 second voicemail, and then bam, it can speak in that exact same voice.
It's like something out of a movie.
Totally. We're talking zero shot, multi speaker, text to speech, TTS for short. It sounds like pure sci fi, but it's real, and it's going to change a lot, especially for accessibility and how we make all sorts of content.
Absolutely. And the stuff you dug up for this deep dive, really cool stuff. We're going to be focusing on a model called your TTS
Right?
and some really fascinating work by NVIDIA in this area of voice cloning,
Yeah,
basically.
voice cloning. Yeah, that's basically what it is.
Right. The goal is to really figure out how this magic works, under the hood, what makes it tick without getting bogged down in all the super technical stuff.
Yeah, exactly. We'll break it down. No PhD required.
Right.
Plus, we've got some like mind-blowing aha moments coming up. For example, how training these models on a bunch of different languages at once, like not just for being multilingual, but it actually helps them get even better at mimicking any voice, even voices in languages they haven't really seen much of.
Yeah, it's kind of wild.
And get this, we're talking about the ability to fine-tune these models with less than a minute of someone speaking. Imagine like your GPS directions being read to you by like, I don't know, Morgan Freeman.
Oh man, that would be awesome.
Right.
Okay, so let's really dig into this. So first things first, what exactly is zero-shot multi-speaker TTS? In a nutshell, it's a system that can take any written text and generate speech that sounds like it's coming from someone it's never even heard before, during training. All it needs is a short audio recording, like a reference sample.
So like a vocal chameleon, it adapts to whatever voice it hears. That's a huge leap from the old TTS systems, right? The ones that sounded all robotic and monotone.
Huge. Yeah. And I think it shows how far we've come. The field has really evolved. Remember how those early TTS systems were designed for one specific speaker?
Right.
And the focus shifted to trying to make systems that could, generalize to new speakers.
Right. Like try to make them more adaptable.
Right. And one of the early approaches involved using things called speaker embeddings. Think of those as like unique digital fingerprints for voices.
Okay, so like a voice print.
Yeah, like a voice print. And models like Takatron 2, they were adapted to use these embeddings, which were a lot of times extracted by a separate speaker recognition model. The idea was to basically give the TTS system a kind of vocal profile to try and match, when it was trying to generate speech.
So it's like saying, hey, TTS, this is what you got to sound like. Aim for this. But it still needed an extra step to make those voice fingerprints.
It did. Now we're seeing more integrated systems, doing it all at once. And that's where your TTS enters the scene.
Your TTS. Enter stage left.
Exactly. So your TTS is built on this VITS architecture, but it's got some new twists, specifically for that zero-shot multi-speaker ability and for handling multiple languages really well. What's really cool is that it's got state-of-the-art results for English zero-shot TTS. State-of-the-art, meaning it's the best we've got so far.
Yeah, it's impressive.
And it's really the first big project that's gone for a truly multilingual approach in this particular area.
So multilingual, does that mean it can like actually understand different languages? Could a voice it learn from, I don't know, English then speak French or something?
Pretty much, yeah. It can work with different languages, even ones it hasn't been explicitly trained on.
Whoa. That unlocks so many possibilities.
Yeah.
Imagine translating books into audio in languages that don't even have a lot of audio data to work with.
That's exactly the kind of thing it opens up. And get this, your TTS has shown that it can actually get pretty good quality and speaker similarity in a new target language, even if it was trained on only one speaker in that language.
So it can learn a lot from just a little, like it can extrapolate.
It's learning those underlying patterns, those commonalities across languages. It's remarkable.
Wow. So what's the secret sauce in your TTS? What makes it so special?
Well, a few key things. First off, like we said, top-tier results in English. Then it's, a pioneer in this whole multilingual zero-shot TTS space. And it can work well even with limited data, like from a single speaker in a new language. And then the fact that you can fine-tune it with like under a minute of speech to really refine the voice similarity, even if the target voice is pretty different from the voices it learned from initially.
Less than a minute. Okay, so walk me through this, right? How does it take text and a tiny voice sample and create realistic speech? Like, is it magic or is it science?
It's definitely science, though it feels a little magical. So your TTS doesn't use those traditional phonemes, the basic sounds of a language. Instead, it just processes the raw text directly.
Ah, so it skips a step.
Right. It skips a step. And this is especially smart for languages that might not have well-established or easily available grapheme to phone converters. Those are tools that, tell the system how to pronounce a written word.
Ah, so it's a shortcut.
It's a shortcut, and it avoids potential errors from that extra step, especially for languages where those tools might not be as good. So let's peek under the hood. Think of your TTS in a few main parts. It's got a transformer-based text encoder. Now, transformers, they're a type of neural network, super powerful. They're great at understanding sequences, like, the order of words in a sentence.
They like to keep things in order. Got it.
Exactly. And they feed in language embeddings, which is basically a bit of information that tells the encoder what language it's working with at that moment.
So it knows if it's dealing with English or French or whatever.
Exactly. And this text encoder, it's got multiple layers, so it really digs deep into the meaning of the text. Then there's the decoder, which uses something called a fine coupling layers and wavenet residual blocks.
Yeah.
These are like specialized tools inside the decoder that take the encoded information from the text and manipulate it, really carefully, step by step, to build up that complex waveform that's human speech.
It's like crafting the sound layer by layer.
Yeah, like shaping the sound, exactly.
So the encoder reads the text, the decoder figures out the sound, but how does it know whose voice to use? Where's the voice cloning happening?
Right. That's where this thing called a variational autoencoder, VAE, and the posterior encoder come in. They're key for the whole end-to-end training. The posterior encoder, it takes a spectrogram, which is like a visual representation of the different frequencies in the audio, and it predicts a compressed representation called a latent variable.
So like a summary of the audio.
Yeah, like a condensed version capturing the essence of it. And this latent variable, along with speaker embeddings, goes to both the decoder and the vocoder. The cool thing is it learns this intermediate representation directly. It skips creating something called a mellospectrogram, which some other models do, and this actually gives better results.
It's like taking a shortcut again.
Yeah, like a shortcut, a more direct route. And then there's the vocoder, which is, in this case, a fancy one called Hi-Fi Jan. It's a neural network. It takes that intermediate representation and creates the final high-fidelity audio waveform. That's the part that actually builds the speech that sounds real,
So it's like the construction crew. They take the blueprints and make the actual building.
Perfect analogy. And your TTS also uses a stochastic duration predictor, which predicts how long each sound should be held. This is vital for natural-sounding speech. We don't want it sounding like a robot reading a shopping list.
I can't unhear that now. A robot reading a shopping list. That's hilarious.
Right. So how about the voice cloning? How does it actually sound like anyone you want? The trick is that the decoder, posterior encoder, and the vocoder, they all get guided by external speaker embeddings.
Okay, those voice fingerprints again.
You got it. These embeddings are made by a separate, pre-trained speaker encoder called HASP. This model was trained on a massive data set of different speakers called VoxCeleb 2, and it's known for being really good at recognizing and telling apart different voices.
It's like the voice expert, right?
Right. And this speaker encoder, it's kept frozen, meaning it doesn't change, during the training of your TTS. So when you want to use your TTS, you give it the text and a short audio sample of, a new speaker. That sample goes into the pre-trained speaker encoder, which creates the speaker embedding, the voice fingerprint.
So it's like providing a vocal blueprint.
Exactly, a vocal blueprint. And then that embedding guides the decoder and vocoder to synthesize the text in that specific voice.
Ah, so that's how it pulls off the voice cloning trick. Pretty clever.
Very clever.
Now, the paper mentioned something called speaker consistency loss, or SCL. What is that all about?
So this was something the researchers explored, adding an extra loss function during training. They wanted to take the audio made by your TTS and the original audio and feed both into that pre-trained speaker encoder, the voice expert we talked about. The SCL tries to make sure the speaker embeddings from those two audio samples are as similar as possible.
So it's like a double check, right? Making sure the generated voice really matches the target.
Exactly, like a quality control check. However, there was a correction issued, an erratum for the paper. Turns out, because of a technical oversight, this speaker consistency loss wasn't working quite as intended in the initial experiments. So even though some results were reported with plus SCL, the full benefit of that loss function wasn't actually realized until later on when they fixed it in the Koki TTS library.
Ah, so a little hiccup along the way. Happens to the best of us.
It does. It does. Part of the process, right? The exciting, sometimes messy process of cutting-edge research.
Totally. So what kind of data did they feed this model to train it, and then how did they test it out?
For training, they mainly use datasets in three languages: English, Portuguese, and French. For English, they use the VCTK dataset, which is about 44 hours of speech from 109 speakers. They also tried out parts of the bigger LiberTS dataset, which has way more English speakers.
So tons of voices for English.
Right. But for Portuguese, they used the TTS Portuguese corpus, which is kind of unique because it's just one speaker, a Brazilian Portuguese speaker.
Just one. Wow, that's a small sample size.
It is. And it really shows you how much potential this tech has for languages with less data. And then for French, they used a part of the MA Lab dataset, which has a few female and male speakers.
Okay, so a good mix of languages and speakers, but how did they know if your TTS was any good? How do you measure the quality of the generated speech and how much it sounds like the target speaker?
They used a few different methods. They had objective metrics and subjective human evaluations, which is, people listening and rating. So for overall quality, how natural the speech sounds, they use mean opinion score, or MOS.
So it's like a rating system.
Yeah, people rate the audio 1 to 5 on how natural it is. For how similar the voice is to the original, they used speaker encoder cosine similarity, or SECS. Remember how we talked about those speaker embeddings, the voice fingerprints? They used a pre-trained speaker encoder called Resemblizer to get those embeddings from both the generated audio and the original audio.
Right, so they compared the voice prints.
Exactly. A higher score means more similarity. And they also did similarity MOS, or SimOS, where people listened to pairs of audio, one real and one synthesized, and rated how similar they sound.
So both computer analysis and human judgment, that seems like a solid approach.
It is. It gives you a more well-rounded view.
What were some of the key findings? Did they find out anything interesting about how well your TTS performed?
Oh yeah, definitely. For the English VCTK dataset, the best speaker similarity, measured by that SECS score, was in the experiments where they trained only on English in the bilingual English and Portuguese experiments.
So sticking to one language or a closely related one seemed to work best.
It did. Overall, the similarity and quality in their best performing models were very close to real human speech, and they did better than other zero-shot TTS models out there at the time.
That's impressive. What about those experiments with the larger LiberTS dataset?
For LiberTS, they got the best speaker similarity when the model trained on the largest number of speakers, including all those from LiberTS. But what's interesting is the best speech quality, the MOS scores, came from the model trained only on VCTK. They think it's because the audio quality in VCTK is generally super high.
So garbage in, garbage out?
Yeah, kind of. High-quality training data is crucial for high-quality output.
What about the Portuguese results? Remember, they only had that one speaker for training data?
Right, just that one speaker. But they were still able to get pretty good quality. Though, they did notice the limited number of female Portuguese speakers in the overall training data had an effect. Seems like adding in data from other languages like French in a multilingual training setup actually helped to make the results better.
Like cross-training for voices.
It's a good way to put it. It helps the model learn a wider range of vocal characteristics.
What about that speaker consistency loss? What happened once they got it working right?
Good question. Their more recent findings show that when it's properly implemented, it does improve speaker similarity, the SECS score. But the impact on SimOS, the human ratings, wasn't always consistent. Sometimes it even lowered the audio quality a bit.
It's weird.
Yeah, it is a bit odd. They think it might be because the model was learning to copy those tiny imperfections or recording artifacts in the reference audio.
So it's like being too good of a copycat.
Exactly. It's like trying to imitate someone's accent, but then you also start imitating their, sniffles or coughs. It might be accurate, but it doesn't necessarily sound better.
I guess you got to find that sweet spot between accuracy and quality. Now, your TTS is also about zero-shot voice conversion, right? What is that exactly? How is it different from the multi-speaker TTS we've been talking about?
So with multi-speaker TPS, you have text and you have a speaker sample, and it generates the text in that voice. Voice conversion it's a bit different. You start with someone speaking, a recording, and you want to make it sound like someone else is saying the same thing.
So it's like a voice swap.
Exactly. A voice swap. You could take a recording of me saying, "Why don't scientists trust atoms?" and make it sound like you saying it.
Of course the answer is
Because they make up everything.
you got it. But how does your TTS actually do this voice swap thing?
Okay, so it doesn't give its encoder any info about the speaker's identity during this process. This forces the encoder to just focus on what's being said, making the output speaker independent.
So it's like stripping away the voice.
Exactly. And then, like in TTS, you give it a speaker embedding of the target voice. And the decoder and vocoder use that to create the audio with the new voice, but keeping the original words.
That is wild. So you're basically swapping out the voice while keeping the words intact. How well did your TTS handle these voice transformations? Did it pass the test?
It did pretty well, especially for English speakers. The results were on par with other top voice conversion models out there.
That's good to hear.
But, like we saw with the TTS results, there were some hiccups with Portuguese voice conversion, particularly with female voices. Again, probably because of the limited training data for those voices.
It's like those voices are harder to learn because there's not enough examples.
Right. And they also tried cross-lingual voice conversion, like taking English speech and converting it to sound like Portuguese, or the other way around. These were also pretty good, although sometimes the quality dropped a little.
Still, it's impressive that it can even attempt that, like bridging the gap between languages. Now, we talked about fine-tuning earlier. Why would you want to fine-tune your TTS with a short audio sample if it already has this zero-shot ability? What's the point of doing extra work?
That's a great question. Zero shot is cool, but it's not always perfect, especially if the new speaker's voice or the recording conditions are way different from what it learned during training.
It's like it's out of its comfort zone.
Exactly. Fine-tuning is like giving it some extra coaching. You adapt it to that new speaker, giving it a little bit of their speech, even less than a minute sometimes.
A little extra practice never hurts.
Right. And the research showed that even these tiny audio samples could make a big difference in how much the generated voice sounded like the target. Really helpful when the initial zero-shot attempt isn't quite there. But there's a trade-off,
Oh, what's the trade-off?
So fine-tuning with a very small sample, say 20 seconds, could really boost the similarity. But sometimes it made the speech sound a bit less natural overall. Using something like 45 seconds or more seemed to give a better balance.
So quality over quantity, I guess.
Yeah, something like that.
Yeah.
You want enough data to make it sound good, but not so much that it loses that natural flow.
Got it. Now, what about NVIDIA? What do they have to say about all this?
Well, NVIDIA wrote this really good blog post summarizing a talk at the Speech AI Summit about, this whole zero-shot multi-speaker TTS thing. They agreed with your TTS research. It showed state-of-the-art performance, and that this tech has huge potential, especially for languages that don't have loads of training data.
Especially those less resourced languages, right?
Exactly. And their Q&A in that post is super helpful, answers a lot of questions people have about this tech.
Nice. Straight from the source. What were some of those questions?
Well, one was about how you measure the quality of these TTS systems. They talked about MOS, SIMOS, and SECS, just like we discussed. And they stressed that even though there's research into using AI to predict these scores, automatically, humans are still the best judges, especially when you're dealing with all these new and different recording conditions.
Yeah, I get that. The human ear picks up on nuances that a machine might miss.
Absolutely.
Another question I have is, could you use those speech-to-text systems, the STT systems, to evaluate TTS? It seems like a logical way to check if the pronunciation is correct.
They actually got that question too.
Yeah.
And they explained that while STT can check pronunciation, it doesn't capture the whole picture of speech quality. Things like intonation, the rhythm, and just the natural flow of speech are super important. But STT doesn't really evaluate those.
So it's like just because you're saying the right words doesn't mean you're speaking naturally.
Exactly. It's about more than just getting the words right. It's got to sound like a person speaking, not like a robot reading a dictionary.
Totally. So how do we get from this awesome research to something other applications can actually use? Could you turn your TTS into like an API?
Absolutely. The Your TTS GitHub repository shows it's built using this thing called the Koki TTS library. This library has tools that let you do both text-to-speech, using a sample of the target speaker's voice, and voice conversion, using both a target voice and some reference audio with the content you want to convert.
So like the foundation is there. How do you then make those tools accessible to other software, make it an API?
You got to build a server application, like a middleman. This server would listen for requests, which would include the text you want, and either a link to the speaker's audio or the actual audio itself. When it gets a request, it uses the Koki TTS library and the Your TTS model to synthesize the speech or do the voice conversion. Then it sends the audio back to the application that made the request.
So it's like setting up a voice generation service.
Yeah, exactly. Like a dedicated service that other programs can just plug into.
what are some things to keep in mind when building this kind of API?
Lots of things. You got to make sure the server can handle many requests coming in at once, and you got to manage all those resources, like loading and running your TTS model, which can be big. And you might want to offer different model options or different languages if you've trained them. Security is a biggie, especially if people are uploading their own audio. Oh, and rate limits, so people can't abuse it. Error handling, too. You got to make sure it handles any problems that pop up.
Sounds like a big job.
It is. But it's cool to see how this kind of research can become something everyone can use,
Absolutely. Democratizing voice creation, that's the future. So, as we wrap up, what are the big takeaways from our deep dive into your TTS and zero-shot multi-speaker TTS?
I think the biggest things are its performance in both multi-speaker text-to-speech and voice conversion, especially in English. The fact that it works across multiple languages is a game changer, opening doors for languages that haven't had this kind of tech before. And the fact that it can adapt to new voices with just a snippet of audio, that's powerful.
Totally. Personalized voices are going to be everywhere, and it opens up so many possibilities for new content in tons of languages.
Well, we got to remember the limitations, right? Like sometimes the rhythm and timing are off, there could be mispronunciations, and there's a risk of bias in languages with less data. The researchers want to improve the duration prediction, train it on more languages, and explore data augmentation techniques to make the models more robust.
Always room for improvement. So, to end this deep dive, something for you to think about. Imagine a world where everyone has their own personalized AI voice. What would that look like? What new things could we do with that? We'll include links to your TTS paper, the GitHub, and some audio samples in the show notes so you can check it out yourself.
That's a great question to leave people with.
And speaking of questions, why don't eggs tell jokes?
I don't know. Why?
They'd crack each other up.
Oh, man. You got me there.
Thanks for diving deep with us today.
It was my pleasure. Until next time.